Hey everyone, Cozy Azeroth, aka Zachary Fruling in real life, and today I'm going to run through Chapter 4 of Beginner's Basic for the Texas Instruments TI-99 4A home computer, my favorite retro computer system, the computer system I had when I was a little kid. I've done Chapters 1 through 3 already, so if you missed those, check those out on my YouTube channel. You can find it under Zachary Fruling or under Cozy Azeroth. And without further ado, let's just dive in. So we're reading through the entire chapter, and we're going to do all the sample programs and exercises from the chapter in the Classic 99 emulator, and I'll put a link to that in the description. Okay, Chapter 4, Fun and Simulations. In this chapter, we'll explore some features of the basic language that allow you to create exciting simulations and games. Many computer programs are simulations that imitate some real-world event. With a computer simulation, we can imitate an event as simple as the rolling of a single die, or as complex as the patterns of animal migration in North America. As an example of a simulation, we'll enter and run a dice rolling program in this chapter. Other programs included here explore the games, graphics, and musical capabilities of your computer. The heart of most games and simulations is the RND function, so let's begin there. The RND function. The letters in the name RND are taken from the word random. To find out what RND does, let's try a few examples in the immediate mode. Clear the screen and then enter this line, print RND. Alright, and I need to get into TI Basic, so let's do that. And we're going to clear the screen, call clear, and it says print RND in the immediate mode. Print RND. And it gives us a random number. Notice it's the exact same random number as in the book, so really what we have here are pseudo-random numbers. Now try entering the line again. We'll get a different pseudo-random number. 0.39133, etc. Yep, exactly what's shown in the book. Let me dismiss the AI assistant. There we go. How far have we come? We now have AI assistants while we're looking at PDFs of an old book. Here's an interesting situation. Every time we use RND, we get a different number. That's exactly what RND does. It generates random numbers. And you can see here, it's only pseudo-random. The first time you run it, you get this number. The second time you run it, you get this number. Same thing as what's in the book. I think there's a way, if memory serves, I'm not sure if it's covered in this chapter or if it's covered in the user's reference guide. There's a way to give it a randomization seed number to make it even more random. Okay, now let's try a program that will produce 10 random numbers. Enter these lines. Okay, so we're skipping line number 10 for some reason. 20 for loop equals 1 to 10. Loop equals 1 to 10. 30, print RND. 40, next loop, and 50, end. Okay. When you've checked your program for errors, run it. A list of 10 random numbers will be printed on the screen. Look at the numbers closely. Are any two of the numbers identical? Okay, let's run it. They should not be identical, I don't think. Doesn't look like it to me, not at a glance anyway. Nope. You may have noticed that all the numbers generated by RND are less than 1, or 1.0, in value. Also, there are no negative numbers. RND is preset to produce only numbers that are greater than or equal to 0 and less than 1. Or 0 is less than or equal to n, which is less than 1. Write down the numbers this program produced and then run the program a second time. Check your written list against the numbers on the screen this time. Very strange, the list of numbers is the same. Okay, let's run. Yep, I don't need to write them down. They are the same. I can look at them here on the screen. This feature of the RND function is important to remember and can be very useful in certain applications. Within a program, RND will produce the same sequence of random numbers each time the program is run, unless the basic statement randomize is used in your program. That's right, I forgot there's a randomized statement that gives you a different set of random numbers. Add the randomized statement shown below to the program that is still in your computer. 10 randomize. Let's do that. Let's clear the screen here. Let's list out the program. including the new line, number 10. So the first line, 10, randomized, spits out a new randomization seed. That way RND generates a different list of numbers. Clear the screen now. Type call clear and press enter. We just did that. List the change program on the screen. We just did that. Run the program again and compare the new set of numbers with your written list from the first program run. Are they different this time? They should be. I vaguely remember the numbers at least. Oh yeah, they're different. I don't remember the exact sequence of numbers, but they are different. What happens if we run it again? Yep, we have yet a different set of numbers. So that's giving us a better set of randomization. Experiment. Continue to experiment with the program until you feel comfortable with RND and randomize. For example, try changing line 30 of the previous program to 30 print RND semicolon RND. Okay. Let's do that. 30 print RND semicolon RND. Okay, let's see what happens. We should get, yeah, two different sets of randomized numbers next to each other. Okay. What result does this change have on the program? If you want the program to generate more or fewer than 10 random numbers, just change line 20. Okay, well, let's do that. Let's have it generate 25 random numbers. So 20 for loop equals 1 to 25. And we're going to print 25 rows of two side-by-side random numbers between 0 and 1. We'll run. And no two should be identical in theory, and it doesn't look like they're identical. At a glance, I'm not seeing any that look identical. Nope, nope. Okay, other random number ranges. The program you just completed generates random numbers between 0 and 1, or 0 is less than or equal to n, when n is less than 1. Now let's examine ways to increase the range of the numbers we generate. Excuse me. The RND function can be used as part of any legitimate computation. For example, 10 times RND and 10 times RND plus 7 are both valid uses of RND in TI Basic. To show what is produced when RND is used in this way, try the following examples. Print 10 times RND. Okay, print 10 times RND. Okay, that should give us a number between 0 and 10, I believe. What number appears on the screen? Try the same example again. What number did you get this time? Okay, print 10 times RND. Okay, 2.7 something. Again, between 0 and 10. In both these examples, you should see a decimal point followed by 10 digits, or 1 digit to the left of the decimal point, followed by 9 digits to the right of the decimal point. That's because 10 times RND produces random numbers in the range of 0 to, but not including 10. Or 0 is less than or equal to n, which is less than 10. Now let's increase the range to this. 0 is less than or equal to n, which is less than 100, or random numbers from 0 up to, but not including 100. Try this. Print 100 times RND. 100 times RND. There we go. And we can do it again. So, random numbers between 0 up to, but not including 100. Okay. Remember, this time you could get 1 or 2 digits to the left of the decimal point in the range from 0 through 99.999 repeating. Let's use a program to generate some random numbers in the ranges 0 to 10 and 0 to 100. Enter these lines. Okay, let's type new, clear the computer's memory. 10 randomize. 20 for loop equals 1 to 5. Oop, I think I typed that wrong. Yeah. Let's go stop the program. I think I made a little error there. Yeah, that looks okay. Okay, 30. Print 10 times RND RND, then I think it had a semicolon, and 100 times RND. Next loop. And 50, I think it was just end, right? Yeah, 50 end. Not necessary, but this book uses it. Okay. I think we're good. Let's see what the book says, though. Okay, so let's see the explanation bubbles here. Every time you run the program, you'll get a different series of numbers. That's what the randomized statement does. A comma here. I used a semicolon instead of a comma. Let's retype 30. 30 print 10 times RND and 100 times RND. Okay, let's list out the program. That looks better. Now clear the screen and run the program. Although the numbers you generate on your screen will be different, they'll look something like this. Okay, call clear and run the program. Yep, so on the left we have numbers between 0 and 10, not including 10. On the right we have numbers between 0 and 100, not including 100 itself. And in theory, once in a very, very great while, you're going to get an even integer. But very, very, very rarely. Study the differences between the numbers in the left print zone on the screen and those in the right print zone. Can you see that the range is greater in those on the right? Run the program again to produce other numbers. Okay, so let's do it. I know we're being a little pedantic here, but let's do it. Book says to do it. Let's do it. Okay, this is an interesting list because we actually get a number that is on the left. All the numbers are between 0 and 10, not including 10. But we actually have a number that's less than 1 even. We have 0.835, blah, 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 blah. And on the right, we have numbers between 0 and 100, but we actually have a number that starts with just 1 point something there on the left. So good illustrations of what this RND function does. Suppose we'd like to eliminate all digits to the right of the decimal point and produce random whole numbers, or integers. Well, do you remember the int function we discussed in Chapter 3? This is a job for int. Change the program by typing and entering this new line. Okay, actually let's list out the program first so we can see exactly what changes we're making here. So 30 print int. So basically it's going to take the whatever result is generated and produce the next lowest integer, the integer to the left on a number line. So 10 times RND. I think we still use a comma. An integer of 100 times RND. So this will produce numbers from 0 to 9 and 0 to 99 and never give you the number 10 or never give you the number 100. Okay. If you list the program now, it will look like this. Let's make sure we got it right. List. Looks pretty good, I think. I don't see any obvious errors. When you run the program, the screen will show two series of random whole numbers. Remember, you won't necessarily see these same numbers on your screen. Okay. Let's clear the screen. Call clear. And run. Yep, numbers on the left are 0 through 9, and numbers on the right are on the right side of the screen are 0 through 99. So not including 10 on the left, not including 100 on the right. All the numbers on the left side of the screen will have values from 0 through 9, while all the numbers on the right have values from 0 through 99. The int function throws away the digits to the right of the decimal point. The following table summarizes what we have covered so far. Program instruction. RND, 0 through 0.9999 repeating. 10 times RND, 0 through 9.99999 repeating. Integer of 10 times RND, int 10 times RND. 0 through 9, integers only. 100 times RND, 0 through 99.99999 repeating. And finally, integer of 100 times RND, the example we just did, 0 through 99, integers only. Notice that all these ranges begin with a value of 0. In many games and simulations, however, we need random numbers that start at some other value. For example, to simulate the throw of one die, you need a random number generator that produces values from 1 to 6. You have seen that int of 10 times RND gives the values from 0 to 9. What would int of 6 times RND produce? change line 30 in the program to print integer of 6 times RND and run the new program. Okay. List. Okay, integer of 6 times RND. So 30 print integer of 6 times RND. Okay, list out the new program. Okay, run the new program. Let's clear the screen first. Run. Okay, 54054. Okay. Random values within a range from 0 through 5. But that's not what we need. Your screen shows a list of 5 random numbers ranging from 0 to 5. What would happen if we added the value 1 to each item in this list? The resultant numbers would range from 1 to 6. That's just what we need to simulate the throw of a single die. Again, alter the program as shown below and run it. Okay. Let's list out the program. We're going to change line 30. So 30, print, let's see how the book structured it here. Integer of 6 times RND plus 1. Integer of 6 times RND plus 1. And that'll give us a random integer between 1 and 6. So let's list out the new program. And run it, it says. Okay, run. Okay, and we get random integers between 1 and 6. Let's run it again. Run it a few times here. We haven't seen a 3 yet, that's funny. It will generate a 3 eventually. There's some 3s, okay. Does work. Everything's an integer between 1 and 6. Okay, simulation of 5 rolls of a die. That does it. The program now in your computer is a simulation or imitation of throwing a single die 5 times. I love they have to define simulation. Now we know what a simulation is, but back in 1977, whenever this book was written, what the heck is a simulation, right? A 2-dice simulation. At this point, we can easily design a program to simulate the throws of 2 6-sided dice. Before you start, erase the old program by typing new, then enter the following program. Okay, new. Let's start typing in a program. Nothing is more 1980s computer than typing in a basic program. So 5, call clear. 10, randomize. This ensures we get a different randomization sequence every time the program is run. 20, input number of rolls. Okay, 20 input, and every time, it's been so many years, every time I do this I have to remind myself of the syntax now. So it's embarrassing because I did do this thousands of times as a kid, but now I have to remind myself. Number of rolls. And we want, I think it was a colon, and look at that number, the numeric variable n. Okay, that looks right. I left some extra space there so it looks pretty. 30 for roll equals 1 to n. 30 for roll equals 1 to n. So we're creating a for next loop that's going to loop over the sequence of code coming up n numbers of times. 40, die 1. Die 1 equals, okay, this is that little equation we had, or formula we had before, integer of 6 times RND plus 1. Integer of 6 times RND, then add 1. Okay. And I think we're going to do the same thing for die 2. Yep. 50. Die 2 equals integer of 6 times RND plus 1. 60, print die 1, semicolon, die 2, comma, die 1 plus die 2. Okay. 60, print die 1, and it was a semicolon. Die 2, then we had a comma, I believe, right? Die 1 plus die 2. Okay. And then 70, next roll. I like the use of descriptive variables here. Oop, I forgot to type 70. 70, next roll. And 80 print. This gives us an extra line. And 90, I think it was just 90, go to 20. And are we using go to run together? We are. Okay. Okay, let's list out our program now. Pretty good. I don't see any obvious errors here. Okay, let's look at these explanation bubbles. So line 20, input number of rolls to simulate. We'll call that n. Lines 40 and 50 simulate the rolls. Line 60, print and display, or display each die in sum of spots. A gambling term here. Okay, semicolon and comma. So far, so good. It looks great. This program prints out the number of, quote, spots on each die and the sum of the spots on both dice faces. Oh, literally just spots on it. It just means spots on it. You were asked how many rolls you wish to make at the start of the program. Run the program now and watch what happens. Run. Okay, number of rolls. Let's do, I don't know, 3 rolls. Okay, so the numbers in the 2 columns on the left, each number is the roll of a 6-sided die, and the column on the right is the sum of those 2 dice values. So 2 and 2 is 4. Die number 1 rolled a 3. Die number 2 rolled a 4. Those add up to 7. On the third row, die number 1 is a 2. Die number 2 is a 1. That's confusing, and those add up to 3 spots. And we can do this until we get bored of doing it. Let's see how many rolls. How about 12 rolls? We got 12 rows here. And the 2 columns on the left are different single die rolls, and the column on the right is the sum of those 2 dice. Okay. I think we get the idea. Let's stop our program. Okay, run. Number of rolls. We saw that. First, the program prints a request for the number of rolls to make. Enter a number, 5 for example, and press the Enter key. Your screen shows 5 throws. The program keeps looping back to the input request line. If you want to stop the program, just press Clear, which is what I just did. Experiment. Try entering different values for the number of rolls. What happens if you try 30 rolls? Then make some changes to the program if you'd like to experiment. For example, how would you alter the program to simulate the throwing of 3 dice? 2 8-sided dice. Oh, okay, this is fun. Let's do both of those examples. So first of all, let's do the throwing of 3 dice. So we'll actually need to create a new variable, die3. Let's call it line 55. Die3 equals same thing, integer of 6 times RND plus 1. Okay, now we need to alter line 60 to display the 3 dice rolls and then the sum of the 3 values. So we're going to rewrite line 60, print die 1 semicolon die 2 semicolon die 3, and then finally we're going to have a comma that bumps us over to the right side of the screen. Die 1 plus die 2 plus die 3. Let's list it out, make sure it looks okay. You can see our new lines inserted there. Die 55, die 3 equals integer of 6 times RND plus 1, gives us a random integer between 1 and 6. And 60, we're going to print die 1, die 2, die 3. Then on the right side of the screen, or the right print zone, we're going to have die 1 plus die 2 plus die 3. So let's run it. And let's do 5 rolls. And here we go. Each of the 3 columns on the left represents each of the numbers in the 3 columns on the left is a single rolled die. All those numbers are between 1 and 6, and in the column on the right we have the sum of the values on the left. So 4, 3, and 4, 3 different dice, and those add up to 11. Second row, 2, 1, and 6, that adds up to 9, so on and so forth. And we can do this as many times as we want. Let's do, I don't know, 15 rolls of 3 dice. Okay. And let's say we were doing a D&D game here, and we have a multi-sided die. So let's list out our program. So let's say we're gonna, what was the next example? 2 8-sided dice. Okay, so we don't need line 55 anymore, so we're gonna delete line 55. And let's list out the program. Every time I make a change, I'm gonna list out the program so you can see what I'm doing here. We need to change lines 40 and 50, because right now those are giving us values between 1 and 6. We want values between 1 and 8. So we need to rewrite line 40. 40 die 1 equals int, and this time it'll be 8 times RND plus 1. And we need to do the same thing for line 50 for die number 2. Die 2 equals int, 8 times RND plus 1. And then we need to edit our print line, because we only have two dice now. So print die 1, die 2, and then comma die 1 plus die 2. I think that'll do the trick. I don't see any errors, but let's list out the program. Okay, that all looks good. Let's run it. So remember, this is 2 8-sided die now, so let's do 5 rolls of 2 8-sided die. So all of the numbers on the left should be between 1 and 8, and at a glance it looks like they are. And the column on the right is the sum of those 2 dice values. Let's do one more, maybe 10 rolls this time. Okay. Let's say we were playing, what was one of those dice value, you know, one of those multi-sided dice that your nephew was showing us? Was it like a 20-sided die or a 10-sided die?
Yeah, he had multiple. Yeah,
let's say a 20-sided.
20.
Is there a 20-sided die? Is that too many?
Yeah,
sides?
no, I think he had a 20.
Okay, so we're going to do 2 20-sided dice here. So 40 die 1 equals int of 20 times RND plus 1. And 50 die 2 equals integer of 20 times RND. Oops, typos, plus 1, there we go. Now let's list out the program, make sure it looks okay. So this will give us 2 20-sided dice and then the sum of the 2 values. Number of rolls, let's just do it once. So here we go, 7 and 11, and that adds up to 18. Let's do 5 rolls. So the values on the left are all numbers between 1 and 20, integers between 1 and 20. And then on the right we have the sum of those two die values. Okay, pretty cool. Error conditions with RND. The error messages produced by an improper usage of RND are essentially the same as the error messages we've mentioned before. Here are some examples. Typing errors, missing operation, error message, incorrect statement in 10. So here we've got a missing operation, just 10 RND. We need 10 times RND. And here we have a missing closed parenthesis, 10 times RND with no closed parenthesis. Same thing, incorrect statement. About the only new error condition we need to mention occurs if you try to use the letters R and D as a numeric variable name in a let statement, let or assignment statement. For example, if you type let R and D equals 5, the computer will respond with incorrect statement. Okay, so let's try that. Let R and D equal 5. Yeah, incorrect statement. So some potential variable names are reserved because they're used for other purposes by the computer. So you can't use R and D as a variable name. This occurs because RND is reserved to be used only as a function in TI Basic. For a list of all reserved words, see the basic reference section of User's Reference Guide. And I'm going to run through the User's Reference Guide in another series of videos. Probably go through one function at a time, do the sample programs, and then maybe we'll do the the fun sort of sample example game programs in the back of the user's reference guide in the separate videos down the road a little bit, so stay tuned for those. Okay, next section, randomized character placement. The following program utilizes the INT and RND functions to generate random screen positions for a character you input. First, type new and press enter to erase your old program, then enter these lines. Okay. Let's clear the computer's memory. So 10 randomize. 20 input character code, or char code, but let's do character code. We'll actually type the whole thing. 20 input character code. And what do we call that? We're going to call that code. 30, call clear. It's a weird choice not to clear the screen first. Oh, actually it's not, because what we're going to do is clear the screen after we input the character code, so we have a nice pretty clear screen to draw the characters on. Oops, I meant 30, call clear. There we go. 40. Okay, so we're basically using random numbers to generate the row and column for the VCHAR function that draws a character to the screen. So row equals INT. Now I should be able to tell what we're doing here. 24 times RND plus 1. That'll generate a random integer between 1 and 24. 24 times RND plus 1. And 50 column equals integer 32 times RND plus 1, because there are 32 columns. Equals INT of 32 times RND plus 1. Okay, 60, call VCHAR, and that is the function that draws some number from 1 to any number, not any number, but some larger number of repetitions vertically of the same character. So we want row, column, and code, I believe it was. We'll check our work here though. Call VCHAR, row, column, and code. Row, column, code. Got it. Okay, and line 70, go to 40. Go to 40. Let's list out our program, make sure it looks good. Looks pretty good. Let's look at our explanation bubbles. So line 40, according to this bubble, produces a row number from 1 through 24. Line 50 produces a column number from 1 through 32. We'll use the character codes 33 through 95, since character 32 is a blank space. We want to avoid entering it when the program asks for a code number. Before running the program, let's examine a flowchart describing its performance. Okay, can we fit all this on one screen? Yeah, there we go. Line 10 randomizes the random number series each time the program is run. Line 20 stops and asks, character code, assigns number you enter to the variable code. Line 30 clears prompting message and input character code from the screen. Line 40 produces a random integer in the range of 0 through 23, adds 1 to value and assigns value to variable row. Line 50 produces random integer in the range of 0 through 31, adds 1 to the value and assigns the value to variable column. Line 60 prints input character in random positions designated by lines 40 and 50. Line 70 loops back to produce new random position for character. Now clear the screen with call clear and run the program. For this first example, enter 42, the character code for the asterisk, as the input for the character code. The screen will look something like this. Asterisks are filling the screen at random. Okay, so call clear, run the program. Even from when I was a kid, I remember that 42 is the ASCII code for an asterisk. And we're getting, this is going to run and run and run until we stop the program. That's very pretty. Randomly generated star field. I love how easy it is to make graphics in this system. That's one of the things I love about it. Okay, you get the idea. I wonder how long it would take for it to fill up the screen entirely. It'd be an interesting experiment just to make this and let it run until every spot on the screen is filled. Eventually, because it's continuing to add an asterisk where there already is one, so it'll look like it's slowing down a little bit when you get new asterisks because you have to wait till it hits a spot that hasn't already been filled. Maybe we'll do that as a separate little experiment in a future video. But you get the idea. Let's stop the program. Not taking too long. Look at that. It's filling up pretty quickly. Okay. Breakpoint at 70. To stop the program, just press clear. Then try running the program several times, putting in a different character code each time. See if any unusual designs are produced. Okay, well, let's run the program. Okay, character code. I don't know. I don't know what these are off the top of my head. Let's try 55. Okay, I'm just gonna fill the screen up with the number 7. Lucky number 7. Here we go. So it's essentially the same program, just with a different character code. You get the idea. Let's run it one more time. I don't know, how about 35? I don't know what that is. Looks like what we used to call the pound sign, now they would call it a hashtag. It's amazing how things change. Number sign. Okay, goodbye hashtags. Revisionist history here, calling that a hashtag. When you've finished experimenting with different characters, let's change the program to generate characters at random, as well as placing them randomly on the screen. First, we'll have to decide how to set the limits we want for the character range. Here's a general procedure for setting the limits for use with RND. Subtract the lower limit from the upper limit, add 1, multiply that result by RND. Find the integer of this result, add the lower limit. So we know we want 63 characters with upper codes ranging from 33 through 95. So our lower limit is 33 and our upper limit is 95. So 95 minus 33 equals 62. 62 plus 1 equals 63. The number we want to multiply by RND is 63, and we must use the int or integer function. So integer of 63 times RND produces random integers from 0 through 62. Now check the limits established when we add our lower limit, 33. 0 plus 33 equals 33, the lowest possible character code. 62 plus 33 equals 95, that's the highest possible character code. Okay, integer of 63 times RND plus 33 will give us random whole numbers in the range we need. Type the following new line. 20 code equals int of 63 times RND plus 33. Okay, so let's stop the program so we can see the change we're making here. So 20, we're defining the variable code. Code equals integer of 63 times RND. 63 times RND plus 33, I believe it was, right? That's right, press enter. Now clear the screen and list the program to review this change. File clear, list. I see someone was spamming our stream here, so I'm going to take 1 minute and report that up. Don't like when people do that. Report. Spam. Spam. Reason spamming our stream. Go away. Submit the report. And we'll block them, yes. Done. Okay. Here is our new program. You can see the new line. Line 20, code equals integer of 63 times RND plus 33. Looks good. I think it looks right. When we run the program this time, the computer will generate a random character code and then print the character in random positions on the screen. Plus, press clear when you want to stop the program. Run the program several times to see different characters. And this time, because the characters are changing as well, the character code is changing as well as the location, when it writes over a blank on the screen that's already been has a character in it, If it's a different character, you'll see a new character replace the old character. Here we go. Different. Oh, that did not. Oh, actually, never mind. It doesn't do it every time. It just picks one random character and then draws that to the screen. We could actually add that in the loop, so every time it generates a different character. But let's run it again. We should get a different character this time. Yeah, letter B instead of a hyphen. Letter B, letter B. Like an episode of Sesame Street here. This episode of Beginner's Basic for the TI-99 4A is brought to you by the letter B. By making changes in 2 lines, you can cause the previous program to print different random characters each time it loops. Try it. Hint, think about lines 30 and 70. Okay, this is what I was talking about. We can actually add that variable, or the definition of the code variable in line 20. We can add that into the loop, and then every time we print a new character, it will print a different character. Okay, so let's get rid of line 20. Actually, what we're going to do, we're actually going to move line 20 into the loop. So we can, I think we can change it to line 35. So we'll clear the screen. Oh, actually, no, not 35. It needs to be after line 40. Because line 70 loops back to line 40. It's not a for next loop, it's just a regular go-to loop. So we need to do it between lines 40 and 70. So let's do it, we'll choose the row, choose the column, and then we'll do line number 55 right before we print the character to the screen. Code equals int of 63 times RND plus 33. And we can get rid of line 20 now. So type 20, hit enter. Let's list out the new program. We're missing line 20, and that's fine. But we've added line 55. Code equals int of 63 times RND plus 33. So every time we go through this loop, this go-to loop, we're going to choose a new character code. And now, every character should be a different character printed to the screen. And sometimes it's going to print a character where there already was one, and we'll get a different character printed there. Let's see if we can catch one in action. I'm not sure if I'm quick enough on the eye to catch when that actually happens, but as the screen fills up, you'll see it happening, I'm sure. Oh, there's one. I just saw one right over here. Let's see if we can catch it again. Yeah, I'm too quick to be able to draw the mouse, so I think it happened right here. If you're watching this on YouTube, put in the comments which ones you noticed most easily. Yeah, so there we go. There we go. Every time it prints a character to the screen, it's choosing a new character code. Fun. I'm not sure I ever ran through this example as a kid. I skipped ahead to the graphics chapter. Okay, the if-then statement. All the programs we've considered so far in this book have been constructed so that they either run straight through or loop using a go-to or a for next loop. The if-then statement provides you with the capability of making branches or, quote, forks in your program. A branch or a fork is a point in a program where either one of 2 paths can be taken, just like a fork in a road. So here we go. We have one path that prints B, another path lets A equals 5. You get the idea. The general form of an if-then statement looks like this. If condition, then line number. The condition is a mathematical relationship between 2 basic expressions. The line number is the program line to which you want the program to branch if the condition is true. If the condition is not true, then the program line following the if-then statement is executed. For example, 30. If k is less than 10, then 70. The statement says, if the value of k is less than 10, then go to line 70 of the program. If k is greater than or equal to 10, then do not branch to line 70. Instead, execute the line following line 30. Let's try a demonstration program. Enter these lines. Okay, let's get a new instance of TI Basic here. Okay, 10, call clear. Oop. 10, we're typing too fast here. 10, call clear. 20, let k equal 1. Okay, 30, print k equals, and then a semicolon and k. Print k equals, semicolon and k. 40, let k equal k plus 1. K equal k plus 1. 50, if k is less than 10, then 30. If k is less than 10, then go to line 30. 60, print out of loop. And 70, end. I'm going to clear the screen, just get rid of the clutter, list the program out. That looks pretty good. I don't see any typos. Okay, so let's see what the explanation bubbles have to say before we run the program. If new value of k is not less than 10, go on to the next line. If the new value of k is less than 10, go back to line 30 and repeat. Okay, so basically we're going to count up until we hit 10, then out of the loop. If it's less than 10, then loop back. Adds 1, so it'll print the numbers from 1 through 10. Once we hit 10, we print out of the loop, and we end the program. Let's run it. K equals up to, actually I didn't print 10, I printed 9. Oh yeah, because it's less than, not less than or equal, just less than 10, exactly. Each time the program reaches line 50, it must make a true or false decision. When k is less than 10, the if condition, k is less than 10 is true, and the program branches to line 30. When k equals 10, however, k is less than 10 is false. The program then executes line 60 and stops. We mentioned earlier that the condition is a mathematical relationship between two expressions. In the example you've just seen, the mathematical relationship was less than, or the less than symbol, or less than. There are a total of 6 relationships that can be used in the if-then statement. Okay, we have equal to, mathematical symbol is an equal sign, the basic symbol is an equal sign. We have less than, we have the less than sign, happily basic symbol is just the less than sign. Greater than sign, greater than sign. Now here's where we get a little funky. Less than or equal to, the mathematical symbol is this symbol right here, the less than or equal to sign, but we don't have that symbol in TI Basic, so we have less than and an equal sign next to each other. Those two symbols next to each other mean less than or equal to. And that still works in a great many programming languages today. Greater than or equal to, same thing. We have this mathematical symbol, greater than or equal to, and we have to use greater than and the equal sign next to each other in TI Basic. And not equal to, in math, we have an equal sign with a slash through it. The basic symbol is the less than and the greater than sign next to each other, and that is not equal to. Suppose we change line 50 in the program to this. If k is less than or equal to 10, then 30. How would the program's performance be affected? This time we're going to count up through 10, I believe. So let's try it. List out the program. And here we're going to say 50 if k is less than or equal to 10, then 30. Let's list out the new program. And if we run it, we're going to count up to 10 this time, including 10. Then we're out of the loop, and the program ends. Now the program prints the value of k all the way through 10, because the new line says, if k is less than or equal to 10, branch to line 30. Experiment. The if-then statement can be a powerful tool in program development. Try this program for a graphics application. Okay. Let's clear the computer's memory. 10, call clear. 20, call color 2, 5, 5. 2, 5, 5. Oh, I didn't type line 20. 20, call color 2, 5, 5. I'm going to clear the screen just to keep it easy on the eyes here. 30, let k equal 1. Equal 1. Keep making typos, sorry about that. 40, call HCHAR, k plus 1, and 42. Call HCHAR, and it was k plus 1, and 42. K plus 1, 42. 50, k equals k plus 1. K equals k plus 1. 60, if k is less than 25, then 40. If k is less than 25, then 40. 70, k equals 1. 80, call HCHAR. K plus 3, and 42. K plus 3, 42. 90, k equals k plus 1. K equals k plus 1. 100, if k is less than 25, then 80. If k is less than 25, then 80. Okay. And 110, go to 110. That'll just hold the graphic on the screen. Go to 110. Actually, did he use did it go to run together? Okay, that's our whole program. See any typos? Not at a glance. Let's run the program. There we go. We got a couple of diagonal lines here. Okay. Which are really just asterisks with the same foreground color and background color. Kind of a quick and easy way to make a square. Let's list that program out. It's going to challenge us to make a change to the program here. Can you follow this pattern to create more than 2 diagonal lines? Oh, probably. Let's get rid of line 110. Okay, so where do we... Basically, we have a couple of lines here. We have let k equals 1. So we basically need to repeat lines. See, we have a sort of a 4-line repetition here. Let k equals 1, call HCHAR, k plus 1, 42, k equals k plus 1, and if k is less than 25, then 40. So it's going to basically create that diagonal line first, then it's going to create the second diagonal line. So now we need to basically do something similar to lines 30 through 60 and lines 70 through 100. So let's add a third diagonal line. 110. K equals 1. 120. Call HCHAR. And here we're going to do K, but we're going to do K plus 5 to bump it over 2 more spaces to the right, 2 columns to the right, and same thing, 42. Okay, and we're going to repeat this if-then statement, 130. If K is less than 25, then this time not 80 or 40, but we're going to go to line 120. No, that can't be right. Let me slow down here. Oh, we forgot to do the k equals k plus 1. That's what I'm missing. K, right, something's not adding up here. K equals k plus 1. Delete all of that. There we go. Now line 140, the if-then statement. If k is less than 25, then we go to line 120 now. And finally, after we've done that, we can say 150, go to 150, and that'll hold the graphic on the screen. So we should get 3 diagonal lines now. 1, 2, 3. Boom. There it is. In fact, you can use this process to create an entire checkerboard if you really wanted to, kind of a large checkerboard pattern, not a checkerboard, but a checkerboard pattern. Cute, huh? Okay. Error conditions with if-then. Like most TI basic statements, if the if-then statement is pretty particular about its form. The main errors that can occur in using the if-then statement are shown below. So here we have 20, if a equals b, then 200, no space after the if. That's going to generate an error. If a equals b, then 200, no space in front of then. Here we are right here. 20, if a equals b, then 200, no space after then. 20, if a equals b, then 200. Invalid relational symbol combination. Like there's no equals in TI basic. 20, if a equals, then there's nothing there, then 200. No expression on one side of the relational symbol. All of the above conditions produce an error message either when entered or during the running of the program, along with a reference to the line number of the statement in which the error occurs. If the line number referenced in an if-then statement does not exist, the program stops and produces a message saying that the line number referenced in the statement is not found in the program. For example, using the line above, if 200 is not a valid line number in your program, you see this error message, bad line number in 20. Games and music. The remainder of this chapter explores color graphics and sound through special games applications. Several of the programs are based on a number guessing game you may have played before. You'll also find that both the RND function and the if-then statement are used extensively in the programs. Okay, a number guessing program. In this game, the computer generates a secret number from 1 to 100 using the RND function and asks you to guess the number. The program tells you if your guesses are larger, smaller, or equal to the secret number. When you guess the number, the program chooses another number and begins the game again. Type new, press enter, and enter these lines. Okay, new. Okay, let's get all this on the screen at once, looks like it. 10, call clear. 20. Secret equals int of 100 times RND plus 1. Secret equals int was what, 100 times RND plus 1. That'll give us a random integer between 1 and 100. 30. Print, I have a secret number. I have a secret number. 40, just print, gives us an extra line. Oops, 40 print, excuse me. 50, input, what is your guess? And we're going to call the inputted number the variable guess. Input, what is your guess? We're going to call that the variable guess. 60. If guess equals secret, then 130. If guess equals secret, then go to line, wait, was it 130? Yeah, 130. 70. If guess is greater than secret, then 100. If guess is greater than secret, go then 100. 80, print too small. Okay. 90, go to 110. 100. Print too big. $110. Print try again. Let's see. Is there a period there? Yep. Try again. Period. Okay, line 20, go to 40. 120, go to 40. 130, print, you guessed it. $140, print, let's play again. Let's play again. 150 for delay equals 1 to 1,000. It's just going to be a little time delay. 160, next delay. And 170, go to 10. Okay, let's read our explanation bubbles. Select a random number from 1 through 100. Your guess is input here. If you guess correctly, the program branches to line 130, which prints you guessed it. If your guess is too large, the program branches to line 100, which prints too big. So on and so forth. Delays, you can read the victory message. All right, run. All right, let's do this. I have a secret number. What is your guess? 50. Try again. Too small. Let's do 75. Too big. Let's do 60. Too big. 55. Too big. 54. Too big. 53. You guessed it. Let's play again. There's our delay. We're waiting. And then we start over. I have a secret number. What is your guess? Let's do it one more time. 50. Too big. Try again. 25. Too small. 35. Too small. 40. I guessed it. Kind of randomly. Didn't have to zero in on it too much. And we're back into the main program loop. Okay, let's end that. Notice that two if-then statements are used in the program at line 60 and 70. In line 60, if the guess is not equal to the secret number, the condition in the if-then statement is false and the program proceeds to line 70. If the guess is equal to the secret number, the program branches to line 130 and prints the victory message. At line 70, we test to see if the guess is larger than the secret number. If the guess is larger than the number, the condition is true and the program branches to line 100. If the guess is smaller than the number, the condition is false and the program proceeds to line 80. Now run the program. Okay, we just did that, but let's see what the book says about it here. Now run the program. When it asks, what is your guess, just type in a number from 1 through 100 and press enter. Here's an example of what might appear on the screen. I have a secret number. What is your guess? 35, that's the first guess. Too small, try again. What is your guess? 75. Guess is too big. Computer says too big, try again. What is your guess? 50. Still too big. Too big, try again. What is your guess? 40. Too small, try again. Aha, must be close. What is your guess? 41. Too small, try again. Is it here? No? What is your guess? 42. Too small, try again. What is your guess? 45. You guessed it. Let's play again. I have a secret number. What is your guess? The computer will start a new game each time you guess the correct number. When you want to stop playing, just press clear. Notice also that we did not include the randomized statement. Therefore, the program will generate the same series of random numbers each time you run it. If you want to make the program create a new set of random numbers each time, just add this line, 15 randomize. Okay, let's do that. Let's list out the program first. Okay. So we want to have a different number every time now, so 15 randomize. List out the program. Here's our new statement, inserted 15 randomize. Now we'll get a different answer every time. Let's do it. Run. What is your guess? 50. Too small. How about 75? Too small. How about 85? Too small. 90? Too big. Okay. 99? Oh, excuse me, 89. 88. 87. I guessed it. This time the answer was 87. Let's play again. So now we're going to get a new correct number. So 50. Too small. Try again. 75. Too big. 65. Too small. 70. Too small. 71. 72. 73. 74. You guessed it. Let's play again. So on and so forth. A tone guessing program. A novel version of the number guessing program can be created using the sound capabilities of your computer. This program generates a random tone from 131 cycles per second through 247 cycles per second. If you need to review the call sound statement and the frequency limits of the computer, see Chapter 1, page 17. Your job is to guess the frequency of the tone. The program lets you know if your guess is lower, higher, or equal to the frequency of the random tone that is generated. When you guess the correct frequency, the program plays the tone 3 times and begins the game again. So type new, press enter, and enter the new program. Alright, this is slightly longer. Let's type it in. New. 10, call clear. 20, tone equals INT, I think it was 247, did he say? Oh no, that's right, we have to do the, we're trying to generate a tone between 131 and 247 so we can actually hear it. Okay, 117 times RND plus 131. Print, here's the tone. Here's the tone. 40, print. $50, call sound. Okay, 1,000, comma tone, comma 2. $60, input guess, please. And I think we called that guess. Yep. Okay, 70. If guess equals tone, then 160. Guess equals tone, then 170. 80. If guess is greater than tone, then 110. $90, print too low. $100, print too high. I'm sorry, 100, go to 120, excuse me. $110, print too high. $120, call sound. $1,000, comma guess, comma 2. It's 1,000 milliseconds, so 1 second, comma guess, that's the frequency. 2, I think, is the volume level. 130, print, try again. $140, print, that just gives us a blank line. Just make it look pretty on the screen. 150, go to 30. $160, print, you guessed it. $170 for play equals 1 to 3. It's going to play the same tone. Oops, excuse me. Going to play the same tone 3 times, as the description indicated. So we're going to create a loop that just counts from 1 to 3. 180, call sound. And this time it was 100, comma tone, comma 2. And this is a tenth of a second now, 100 milliseconds. 190, next play. So it sends us back to the beginning of the loop. 200 for delay equals 1 to 500. This is going to create a little time delay here. 210, I think it's probably next delay. Yep, next delay. And finally, 220, go to 10. That starts the program over again. 220, go to 10. Okay, let's see what the book says. Line 20 may need a little explanation. If the lowest tone we want is 131 cycles per second and the highest is 247 cycles per second, how do we set our random number limits? Well, int of 117 times RND produces numbers from 0 through 116. 0 plus 131 equals 131, our desired lower limit. 116 plus 131 equals 247, our desired upper limit. Now run the program. The information that appears on the screen is similar to the number guessing program. The only difference is that in this program, your guess is played back to you by the computer. Well, let's run it. Here's the tone, okay? What was it? I gotta remember the limit here. What were the limits? It was 131 to 247. Okay, so let's do, I don't know, 170? Too low, try again. Here's the tone. Okay, 170, 190. Too low. 195. Too high. 193. Too high. 192. And it goes dit-dit-dit, like the letter S in Morse code. Okay, get the idea there. We don't need to belabor that one. If you'd like to change the tone limits, you can do so easily by changing line 20. For example, suppose you'd rather hear a series of higher tones, perhaps in the range from 262 cycles per second through 392 cycles per second. How would you rewrite line 20 to generate these tones? Yeah, I'm always really bad at this, actually. So let me, look at line 20. Okay. I gotta remind myself how this works. Right, so that is the desired upper limit, right? Oh, sorry, the lower limit. 0 plus 131. Right. So let's rewrite line 20. Okay, so let's start the program. What were the limits we're aiming for now? 262 to 392. Okay, so I think what we need is, I need a piece of paper here. I'm not good at this in my head anymore. So we need something like tone equals int of something times RND plus, we want our lower limit to be that addition. So the low limit is going to be what? 262. And we want our upper limit so we need so we take our upper limit minus this number and then plus 1, I believe. Right, so 247 minus 131 and then plus 1, that gives us 117. Okay, so here we want 392 minus 262 plus 1. So bust out the old trusty calculator. 392 minus 262 plus 1, 131. Okay, let's type that in. Tone equals int of, we said it was what, 131? 131 times RND plus, we said it was going to be 392. Is that right? No, it was the, that's why every time I do this I have to look it up, plus the lower limit. So we want it between 262. Right, plus 262. There we go. That should do the trick. So if we run it now, yes please. Oh, I don't know. What were our limits again? It was 262 to 392. Let's do, I don't know, 310 to start? Too low. Let's do 330. Too low. 335. Too high. 333. Too high. 332. It's going to make us work for this one. 331. There it goes. Did-did-did. Letter S in Morse code. And there we go. Alright, we belabored that one. And I'm not good at that part. Okay, color up. Next, let's examine two color programs. The first program creates 10 randomly placed horizontal bars of a color you input and of random lengths. Then the program stops for you to input a new color code. You'll notice that we've used if-then statements in a new way, lines 30 and 40. We test the input color of the code to be sure it's valid. If it isn't, the program gives you a specially written error message. Okay, let's type this one in. New 10 call clear. Nope. Typo. 15 randomize. 20 input color please. And we're going to call that C. 25 call clear. 30 if C is less than 1, then 200. C is less than 1, then 200. 35, if C is greater than 16, then 200. Let's find 35, I think, right? Yeah. 40. For a loop equals 1 to 10. 1 to 10. 45, row equals int 24 times RND plus 1. 50, repeat equals int of 28 times RND plus 1. Okay, 55, call color. Manuate. 55, call color 2, C, C. 60, call HCHAR, row, 3, 42, repeat. Row, 3, 42, repeat. 65 for delay equals 1 to 100. $70, next delay. 80, I believe, was next. 75, excuse me, next loop. There's a loop inside of a loop there. 80, go to 10. Okay, 200. Print. Bad color code. $210, print must be 1 to 16. Must be 1 to 16. $220, print try again. Actually, wants an exclamation mark there. It doesn't really matter. Let's get it right. Print try again. There we go. 240 for delay equals 1 to 500. 240, did I miss a line? Oh no, just don't have a 230 there. For delay equals 1 to 500. $250, next delay. And $260, go to 10. Okay, let's see what the description bubbles say. Okay, test the input color code, right? We're checking to make sure it's between 1 and 16. Generate a row from 1 through 24, row number from 1 through 24. Generate a random number of repetitions from 1 to 28. Print the color bar. Special error message for invalid color code, and so on and so forth. When you run the program, you'll see all of the bars begin at column 3 near the left-hand edge of the display. Their lengths, however, are random, as are their horizontal positions on the screen. After 10 bars of the input color are placed, the program clears the screen and asks you for a new color code. All right, let's remember to avoid putting in color codes 1, transparent, and 4, the screen color in the run mode. Although these are valid codes, you won't be able to see the bars. Okay, let's run it. Color, please. How about magenta? 3, 4, 5, 6, 7, 8, 9. There we go. Color, please. Different color code this time. How about white? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, so sometimes it's choosing a row where there was already a color bar. Okay, now let's check what happens if we do an invalid number. What if we type 0? Bad color code, must be 1 to 16. Okay, color please. How about 19? Bad color code. 247, bad color code, must be 1 to 16. Try again. Okay, how about a darker green, 13. So it's printing horizontal bars at 10 different locations. Sometimes they overlap. Get the idea? The next program is a game that can test two colors against each other. A winning color is randomly chosen. The program is the longest you've seen yet, so we'll provide some explanations as we go along. Here's the program. Okay, let's start typing. That's the thing about these type-in programs, they take a while. Let's do it. 10 call clear. 20, I think it's done by 10. Yep, 20 input first color. We're going to call that C1. 30, if C1 is less than 1, then 700. 40. If C1 is greater than 16, then 700. 50, input second color. And we'll call that C2, I believe. Okay, if C2 is less than 1, if C2 is less than 1, then I think it was a different line number this time. 800. 70. If C2 is greater than 16, and I think it was the same line number, 800. Let's check. Yep. 80, call clear. Clear the screen. 90, color test. Color test equals integer 2 times RND plus 1. Pick randomly either color 1 or color 2. Okay? 100 for a loop equals 1 to 50. For a loop equals 1 to 50. Set loop to print 50 colored squares on screen. Okay. 110. Row equals int 24 times RND plus 1. 120. Column equals, oops, I can spell column with an N, equals, I think it's int of 32 times RND plus 1. Let's double check. Yep. 130. If color test equals 1, then 160. Then 160. 140, let A equal C2. $150, go to 170. $160, let A equal C1. Line 170, call color. 2, comma A, comma A. $180, call HCHAR. Let's check what we have here. Row, column, and 42. Row, column, 42. 190, next loop. $200 for delay equals 1 to 500. $210, next delay. $220, go to 10. And now we skip a bunch of lines. We're going to use our error messages here. 700, print bad color code. $710, print must be 1 to 16. Must be 1 to 16. 720, print. This probably says try again. Oh, cannot type today. There we go. Try again. 730, go to 20. Okay. 800, print bad color code. Oops, keep reading my exclamation or my quote marks here. Bad color code. 810, print must be 1 to 16. 820, print try again. 830, go to, in this case it's line number 50. Go to 50. Okay, I think that is all. Let's look at the explanation bubbles though. Accept the first color code and check for validity. Accept the second color code and check for validity. Pick randomly either color 1 or color 2. Set loop to print 50 colored squares on screen. Select random position for color square. If color 1, quote, wins, branch to line 160 and assign value of C1 to A. Color 2, quote, wins, assign value of C2 to A and go to line 170. Print the color square in random position on the screen. Go through loop again until 50 squares are on the screen. Delay to observe the pattern, then start new game. Print error message if color codes are invalid. Okay, let's see. Two people can play against each other, or you can play against yourself by putting in both color codes to see which, quote, wins the game. Avoid entering color codes 1 and 4. Alright, let's do it. Run. First color, I don't know, 13. Second color, 14. So let me look at this program one more time here. What is the purpose of this? Oh, I see. So it just randomly chooses a winner. Okay. Got it. Okay, well, let's run it. Let's generate the error messages. 0. Bad color code. Try again. First color. 5. Second color. Let's pick something invalid. 76. Bad color code. Second color. 2. Black. Okay, and black 1 this time. All right. I'm not sure I ever bothered to type that program in back in the day. Random notes. Let's see how many more programs we have to go here. We're getting there. Yep, we're almost done. So let's blaze through the last couple programs here. So let's type new. Random notes. We used call sound earlier in a program that played notes from a musical scale. See chapter 2, pages 39 through 40, or check out my chapter 2 video. If we modify that program, adding the if-then statement and the RND function, we can make the computer play some interesting but not necessarily enjoyable, quote, music. Here's how. Let's do it. 10. Let. C equals 262. 20. Let. D equals 294. Oop, I'm sorry, 15. Let D equals 294. 15. Let D equals 294. Now 20. Let E equals 330. These are the frequencies for these notes. 25. Let F equal 349. 30. Let G equal 392. 35. Let A equal 440. Oops, 35. Let A equal 440. 40. Let B equal 494. Sorry, I already forget the number. 494. 45. Let C2 equals 523. High C, in other words, equal 523. Okay, 50. Randomize. 55. Note equals INT of 8 times RND plus 1 so it generates an integer between 1 and 8. 60 time equals INT 901 times RND plus 100 according to the notes here. That generates a duration from 100 through 1000 milliseconds. Okay, 65. Volume equals 2. I don't know why I was obsessed with the number 2 for volume in these programs. Okay, we have a bunch of if-then statements. Okay, 70. If note equals 1, then, was it 200? These go up by 100s, right? Okay, then 200. And we're going up by 5s, yep, 75. If note equals 2, then 300. Oops, 300. 80. If note equals 3, then 400. 85. If note equals 4, then 500. 90. If note equals 5, then 600. 95. If note equals 6, then 700. I want to make sure I'm on track here. 100. Yep, still going up by 5s. Okay. 100. If note equals 7, then 800. 105. If note equals 8, then 900. And that's all, right? Just double check where we're at. Oh, nope. 1 through 7. Here we didn't. 105. What did I miss here? Oh, look, we skipped a line. I don't know why these programs skipped a line. That's what was confusing here. Okay, so we need to retype. We need to get rid of line 95. Let's list our program. We need to retype line 100. 100 if note equals 6, then 700. 105 if note equals 7, then 800. Let's list it again, make sure we're on the rails here. Okay, 110, otherwise note equals C2. Okay. $115. Call sound time note volume. $120, go to 55. Okay, now we're in the different branches here. 200, note equals C. 210, go to 115. It's 115, yeah. Okay, now we basically do the same thing for all the other notes, right? Okay, 300, note equals D. 310, go to 115. 400, note equals E. 410, go to 115. 500, note equals F. 510, go to 115. 600, note equals G. 610, go to 115. 700, note equals A. 710, go to 115. And 800, note equals B. 810, go to 115. Notice we already have the case where it's a high C covered up here. So if it's not one of these notes, then it gets high C or C2, plays that note. Otherwise, it defines the variable note, goes back and plays the sound. Is there anything else, or is that the end of the program here? I think that is the end of the program. Now run the program and enjoy the quote music. When you're ready to quote stop the music, just press clear. So this is going to be kind of weird. It's going to generate a bunch of random tones on the standard C scale and random lengths. So let's see what we get. It's musical-like. It's not unpleasant. And if we run it again, because we used the, what's list, we did use the randomized code, right? Yep, randomized. So when we play it again, we're going to get a totally different progression of notes. So we'll list out the program. We'll play it again here. Run. And this will just go on and on and on until we stop it. It's actually, it is musical. It's there's some seeds of something great there. You might like to experiment with this program in various ways. For example, do you notice anything different in the music if you change lines 60 and 65 to time equals 500 and volume equal 5? Okay, so 60, time equals 500, and 65, volume equal 5. Volume equals 5. Okay, let's see what we notice. This time all the notes are equal length. Sometimes it sounds longer because we're getting two notes of the same strung together with no space in between. Okay. A musical interlude. Now that we've let the computer play its music, let's play some music of our own. With this program, we can use the keyboard to input the notes we want to play. Enter these lines. Okay, this will be fun. This is a short little program. New. 10, call clear. $15, let C equal 262. 20, let, oops, hold on here. I have a typo here. 15, let C equals 262. There we go. 20, let D equals 294. 25, let E equal 330. 30, let F equal 349. 35, let G equal 392. 40, let A equal 440. I knew that one, I didn't need to look it up. 45, let B equal, everyone knows A is 440. Let B equal 494. Of course, these aren't exact. Some of these are actually fractional in real life. 494 is that what it was? Yep. Okay. 50. Input note, and then call that A string. Input note. Just to make it a little prettier, maybe we should put a colon inside there. Yeah, how about something like this? Note A string. That'll look just a little prettier. Okay, do 55. If A string equals, now here's where we need to, okay, equals C, then go to line 100. And these go up by 100 increments. Okay, then 100. 60. If A string equals D, then 200. 65. Make sure these line numbers go up by 5 here. Yep, all the way there. Okay. If A string equals E, then 300. 70. If A string equals F, then 400. 75. If A string equals G, then 500. 80. If A string equals A, then 600. And 85, if A string equals B, B in quotes, then 700. Sure I got that right? Yep, 90, go to 50. Okay, 100, note equals C. And then 110, go to 800. All of these go to 800. Okay, 200, note equals D. 210, go to 800. 300, note equals E. 310, go to 800. 400, note equals F. 410, go to 800. 500, note equals G. 510, go to 800. 600, note equals A. 610, go to 800. 700, note equals B. 710, go to 800. Make sure I got that right. Yep. And otherwise, oh, actually, no, what do we do? What do we do wrong here? 700, note equals B. Yep, okay. So 700, note equals, we've exhausted all the other cases, so 700 just says note equals B. There is no 710. So 710 can go away. And 800, call sound. And here we have 100, comma note, comma 2. And 810, go to 50. Return for a new note. Okay, when you run the program will ask you for a note. If you then press one of the letter keys, A, B, C, D, E, F, or G, followed by the Enter key, for example, when the screen shows note, cursor blinks until you enter a note, and you press these keys, A, and enter, the note A will play. The screen keeps a record of the keys you press. Okay. Let's do it. Run. Note C, D, E, F, G, A, B, and then we're back to C. Now if you hit something else, like an H, it just says nope, it doesn't like that. That's just, that beep you're hearing is just the sound the computer plays when it's asking for an input. So let's do B, E, how about C, C, E, G, a C chord, so on and so forth. Okay. Having to press the Enter key for each note slows down your musical performance a bit, doesn't it? What can we do about this problem? The call key routine. There is a routine that permits the transfer of one character from the keyboard directly into a program. The routine is call key. If you alter the current program in the following way, you don't have to press the Enter key after hitting the key for each note. Okay, so we have to change a few things here. Okay, enter 50, call key, 0, comma note, comma status. 0, comma note, comma status. Okay. 55. If status equals -1, then 50. 60. Okay, if status equals 0, then 50. Okay. Sure got this right. 50, 55, 60. Yep. Okay. 65. If note equals 67. If note equals, this is key number 67 now. Then what do? We go to 100. 70. If note equals 68, then 200. 75. If note equals 69, I believe. Let's just double check. And 300. Let's make sure these are sequential here. It should be. Almost. Then we get circle back to 65 and 66 for A and B. Okay. 80. If note equals 70, then 400. 85. If note equals 71, then 500. And 90, got to be careful here. 90, if note equals, this is the code for, the key code for A, 65, then 600. And 95, if note equals 66, then 700. Okay, so we have some new things here. Character code of depressed key ends up here. That's the note variable. Status indicator. If it's 1, that's the new key since last time. Oh yeah, I think something's cut off here. One of these is -1. I think 1 is new key since last time, -1 is the same key since last time, and 0 equals no key depressed, I think. Okay. Then we check the character code to see if it's one of the following keys, A through G. Here's how call key works. Before we run it, let's read the explanation. Each character on the keyword has a numeric code. When a key is depressed, the character code of that key is assigned to the second variable in the key routine. In this example, the character code is assigned to the variable note. The last variable in the key routine is a status indicator. The indicator lets the program know what has occurred on the keyboard. If you keep holding down the same key, the status is -1. If you press a key different from your last entry, the status is 1. If you don't press any key, the status is 0. When you run the program, nothing appears on the screen as you press the keys. The program simply plays the note you request. So go ahead, make a little music. The call key routine allows you to create, quote, your own kind of music, and the routine can also be used in many games and simulations where single character input values are requested. The call key routine speeds up the input of data by eliminating the need to press enter, the enter key after your data entry. So let's run it. Let's make a little music. So let's see if this works. C, D, E, F, G, A, B, and C. So we could play a little music. Okay, here we go. Twinkle, twinkle, little star. It's much harder when you're not doing it on a piano. You gotta think about which key to press. So. Oops. There we go. A little imperfect rendition of Twinkle Twinkle Little Star, thanks to the call key routine. Alright. I think that is all for Chapter 4. This chapter has given you an idea of the many interesting games and simulations you can develop with your computer. You've discovered these new features. RND allows you to generate random numbers. Randomize ensures that each series of random numbers generated by a program will be different. If then provides conditional branching capabilities in a program. Call key permits the transfer of a keyboard character directly into a program without pressing enter. Congratulations, you've accomplished a lot of computer programming. The following chapter deals only with computer graphics. You'll learn how to define your own characters and how to make animated patterns on the screen. Just turn the page for some more exciting experiences. So that is the end of Chapter 4 of Beginner's Basic. And for my next video, when I get that far, some days hence, hopefully not weeks hence, days hence, I'll dive into Chapter 5, Computer Graphics, which was a chapter I went back to a lot when I was growing up. In the meantime, thanks for tuning in to Chapter 4 of Beginner's Basic. Remember, I used the Classic 99 emulator for this run through of this chapter. I'll put a link for that in the description. Be sure to check out my YouTube channel, Zachary Fruhling or Cozy Azeroth. You can find it under either one. Also, check out my Twitch channel for live streams, some retro programming for the TI-99 4A. We're working on a retro 8-bit video game in Pico 8. I stream World of Warcraft quite often and some various other games. Streaming 5 out of 7 nights a week, somewhere in there, several times a week at this point. Anyways, thanks for tuning in. Be sure to check out my YouTube channel and Twitch channel, and you can find me in various other places under Cozy Azeroth, Discord and whatnot. Hope everyone's having a good day, and I will be back subsequently for Chapter 5. And we'll and then after I finish up the beginner's basic guide, I'm going to move on to the user's reference guide. There's a lot of cool stuff in the user's reference guide that isn't documented on YouTube, so I want to try to document some of my favorite retro programming tools out there on this system. In the meantime, hope everyone has a good day, and thanks for tuning in. Catch you next time. Bye bye.